we have the same reagent, in this case, Alama blue. And if it is oxidized, it is blue and does not have much fluorescence. If it is reduced, then we have the change of color to pink, and we have the increase in fluorescence intensity. Okay, so the previous lab, you were looking at the proliferation rates and how the proliferation affects the absorbance of these cells, or absorbance of the Alama blue. Now we are going to look at the viability of the cells, because let's say again in pharma, you could start with 1,000 chemicals, and of course you cannot use them on animal models. You will need to have some kind of fast track to see if some of them are actually killing cells. And what you do, you have the cells that you seed in your experiments, and then you see if these cells die because we add these chemicals. Okay, it's not only related to pharma, but the pharma is a very usual example for these type of cytotoxicity tests, etc. If you go to the lab and you work with a group that has a particular interest in nanoparticles, you will see these cell viability assays all the time, because they use different cell types, even different types of cancers, just to understand what nanoparticles are best hits for this particular type of the cancer. So these everything like testing of drugs, testing of chemicals, testing of everything. Let's say you are studying siRNA. Of course, you want to know if this siRNA is effectively works on your cells and does not kill them, because if this siRNA degrades some very important, let's say, acting messenger RNAs, the cell dies because it does not have the very crucial player of the cytoskeleton. And of course, you cannot use this siRNA. So you are going to perform this cytotoxicity test with your siRNA. So this everything is related to understanding how stressed your cells are. Okay. So again, cytotoxicity is the measure of the living cells being stressed and undergo the apoptosis or usual necrosis. Okay, so what you do, again, you use your Alama blue because it's being reduced when we have a viable cell. Okay, so why do you need to have this cell cytotoxicity or in vitro cytotoxicity tests? Because again, if you use 1,000 drugs to test, you will not be able to use 1,000 mice or monkeys or even people to test these drugs. First, you need to understand how they behave in vitro. And in vitro is very cheap and ethically approved way to see the cytotoxicity. Of course, sometimes you will need to go very specific on cell types, because as you understand, we have different tissues, and different tissues, they differ in terms of uptake or endocytosis, also their metabolism, etc. So let's say that you are doing, you are investigating some drugs that affect the heart. So what is in heart could be affected. It's muscle tissue, the endothelial cells, and I mean the vessel cells, and lots of connective tissues. So these all could be affected by a drug. And of course, you want to know very specific effects of this drug on these cells, okay? That's why you want to perform different cytotoxicity tests on different cell types, etc. And in this case, of course, you don't get the full picture of how it's going to affect your heart, but at least you understand how it affects different tissues that are comprising your organism or your organ. Of course, it's fast, it's easy, and in terms of financial stuff, it is cost effective because growing one mice is really expensive. And again, you cannot use all those drugs on mice. You have to first define the toxicity on usual cellular organisms. Okay, so what are the limitations? The limitation is, first of all, metabolism of the whole organism, because let's say that we have okay, so we give a person some kind of drug, and the person actually has an ability to neutralize it in the liver, okay? And if it neutralizes it in liver, then we don't have any of those adverse effects or cytotoxic effects. But if you do it in the, so here we have organism, and if we give this drug to, let's say, epithelial tissue, of course, we have the killing of the cells, so cytotoxicity. So we don't have a full picture when we just use the in vitro studies. And of course, it leads to the question that after some investigation or after some research, we need to proceed to the next level, which is the organoids. If everything is okay on organoids, then we can try the animals. If everything is fine on animals, we can switch to the small group of volunteers, then to a bigger group of patients. And finally, we actually introduce this drug to the community or to the humankind. Okay, so these whole effects of in vivo administration of the drug is really dependent on the metabolism of this particular chemical. Of course, we cannot study the lifelong toxic effects on these cell cultures. Why? And I do think that you have heard about one diabetes drug that was given in 50s of the 20th century. And this diabetes drug, it was curing or helping people, not curing, but helping people. And also it would initiate the mutations in embryos, which means that they wouldn't have hands or other limbs, or they would really lack in terms of the development of the brain. Okay, so what else? On the cell culture, you cannot see the distribution of the chemicals in organs and tissues. Of course, you could also understand it. So let's say that you are using some hydrophobic chemical, and you could expect it to be distributed easily by diffusion in subcutaneous fats, in where else? In the bone marrow, in brain. So these everything are possible targets for the hydrophobic drugs. And of course, you need to foresee those distribution before you start the animals and small patient groups studies. Okay, so when you also use this in vitro, you cannot predict the routes for chemical entry, because let's say that you have a drug that should be given per os, but because of its hydrophobicity, it starts diffusing into the organism through the skin. Of course, you cannot predict it if you just use the epithelial tissue or whichever. Okay, so another part is toxicokinetics, and this is a huge part of the medical pharmacy, and they study the uptake, the clearance, and half-life, etc., etc. So lethal dose 50. This everything is studied only on animals and people. Okay, these are limitations of the drug testing in vitro. But what else we could do? And you already done the trypan blue studies. And in this case, you just see the dead cells, then you count the total number of cells and you identify the number of dead cells per 100 total cells. And of course, it gives you the rough picture of the viability of cells. But the thing is, if you have 1,000 drugs to test, you will need to count the viable and non-viable cells 1,000 times. And of course, it's time consuming, etc. That's why the assays were developed. So one of them is lactate dehydrogenase assay. In this case, it shows the presence of lactate, shows you the stress levels of your cell culture. Another method is MTT assay or Alama Blue assay. So these are related to metabolism, and these MTT and Alama Blue, they get reduced, and because of this reduction, they change their characteristics. In Alama Blue, it's the change of color and intensity. In MTT, it is solubilization. So in this case, MTT sediments as crystals. And then after you dilute it in DMSO, you can actually measure the absorbance, and by these absorbance, you could obtain the number of cells, etc., etc. So you could also try to see apoptosis in the cells. So by using annexin 5, this annexin is the antibody that senses the phosphatidylserine, and this phosphatidylserine is being expressed on plasma membranes in apoptotic cells. And of course, in this case, you see the perfect counting of apoptotic and non-apoptotic cells. If half of your cells are undergoing apoptosis, then you might have problems with the treatment that you give to the cells. And finally, ATP assay. Of course, you understand that dead cells, they don't have mitochondria and they cannot produce ATP. Okay, well, mitochondria only in aerobic breathing. If you talk about the anaerobic glycolysis, of course, you understand that two molecules will be created in the breakdown of your glucose. But again, if the cell is non-viable, then they don't produce it at all. Okay, so the experiment itself, so we have the setup. We use the prostate cancer cells, so DU145. And what we are seeding here, first of all, we seed the non-treated or untreated cells. So in this case, we add cells, but we do not add the treatment. Then we have different concentrations of treatment, and, which is very important, we need the blank. And blank here is no cells and just addition of Alama Blue. Why? Because blue or oxidized Alama Blue has very low intensity of the fluorescence. So it should be perceived as the background intensity of fluorescence, okay? So what you do, you seed 50K per 50K cells per well in your 24 well plate, and you will have 2 data sets, okay? So what do you have else? Of course, you are using triplicates because you want to understand the mean, the standard deviation, etc. If you use bigger plate with a bigger number of wells, you can go more than triplicates, like quadruplicates, etc. up to 9 wells occupied by the same condition. And of course, in this case, the precision of your experiment rises, but the least number of treatments or wells per treatment is 3, because in this case, of course, mean is calculated easily. Okay, so what is urea? And we're using it as the treatment. So the urea, if you remember, it is the first organic molecule that was synthesized in the lab, and it actually kind of the start of organic chemistry in the world. So when we understood that these organic molecules, they can be created in the lab, we started investigation on organic chemistry, etc. So what do we have? We have the reaction that includes CO2 and 2 ammonium, and it gives you CH4 and 2O, which is urea plus H2O. So this is a simple reaction, but this reaction actually reduces the toxicity of 2 ammonia to the toxicity of this urea. And if we eliminate it very fast, it will not affect our body. Okay, so it is it exists in the lab as a powder. Of course, first you need to get these molar concentrations, you need to solve it. And of course, it does not matter what you use because it's highly soluble in water. So you could use water or you could use DMAM. And in our case, we're going to use DMAM because our cells will be living for 24 hours in such environment. And of course, they still need albumins, they need growth factors, etc., etc. Okay, so what do we have about the urea? Urea is the colorless crystals, white in color, if they are colored. So they are highly soluble in water and they denature proteins. Okay, so they unfold the conformation. And that's why it is being toxic to our body. So it can lead to irritation of skin, eyes, and epithelial tissues. So if you inhale it or swallow it, of course, you will have problems. So it could be used as the fertilizer because some organisms use these as the source of nitrogen. Okay, so what happens when we have, well, why we have the production of urea in our organism? So of course, you understand that protein comes to the body with the food or by the destruction of own tissues. So what we do, we first break down the proteins into amino acids, and then amino acids, they can undergo some synthesis or breakdown, and we have lots of the ammonium being produced in this breakdown or degradation of amino acids. And since it is highly toxic, we need to inactivate it or detoxicate it. So what we have the special organ called liver. And in this liver, we have addition of CO2 and 2 ammonium molecules with the output of water. And then we have this urea. So this urea, again, if it is being discharged from the body very quickly, then it does not give us any harm, okay? So we have some urea in the bloodstream, and when the blood goes through the filtration in the kidney, this urea is being excreted as the urine. So we might have 2 different conclusions if we obtain some urea or ammonium in our blood. Okay, so we are talking to somebody, and I want to hear Karina Ibrahimova. Karina, are you here? Okay, Karina is absent. Then we talk to Zeria.
Yes. Can you repeat the question, please?
Yeah, so no, I didn't say it. Okay, so the question is, if you have high urea in the blood test, what it might tell you?
So it might mean that you have some pathologies, maybe.
With what?
With
Pathology
kidneys.
of what? Yes, of course. So if we have accumulation of urea, it's the problem of kidney. So what might be the solution to this problem? Zeria?
Yes, I'm thinking maybe special treatment.
Yes, of course. So first of all,
Yes.
sorry. First of all, you undergo the diagnostics because it might be transient or temporary failure of kidneys, or it might be actually stable failure of kidneys. Okay, so the approach is different in transient and stable failure. If it's transient, then of course we can treat it, but if it is stable, what you do? It is the question from MB1. Okay, just suggest something because it is not a quiz and you just give a suggestion.
So you're asking what should we do if the high urea is constant? Yeah.
Yes,
what?
If it is a stable failure of kidneys, what you might
maybe
do to help the
replacement
person.
of the organ.
Transplantation is one of the ways, but much more accessible one, because you know the transplantation usually leads to, not usually, but sometimes leads to rejection of the transplant, and it might be a problem for the person, I mean the patient. So what else we could do before we send the person to transplantation?
Maybe provide him special treatment that has some substances that can filtrate this high urea.
So how it's done? There is a whole method that you learned during MB1 that is related to filtration, etc. So if you guys can help Zare, you just can say it.
It's dialysis.
Yes, of course, hemodialysis. So you could try hemodialysis here, because if the person does not really overwhelming urea concentrations, they can still survive in the stable failure of the kidney, but undergoing this hemodialysis every 2 weeks. And of course, it reduces the quality of life, but at least they don't die. Okay. So the next question is about high ammonia. So we are talking to Abdullahan. Are you here? Okay. Oh, you don't have the microphone, right? Okay, so we are talking to Dana Bigazina.
Yeah.
Okay, so you have high ammonia. What it tells you?
The problem must be with liver.
Yes, of course.
Since it doesn't synthesize urea from ammonia. So
Yes.
I don't know about treatment, probably like to adjust the diet.
Before the diet,
I don't know.
etc., you first need to undergo the diagnostics. Okay.
Oh, yeah.
So when you have the diagnosis, you have two types, again, transient and stable failure of liver. And depending on the stable or transient, you give the recommendations. If it is transient, let's say the person has hepatitis A, of course, they will need to check their diet, go through some treatment related to viral elimination, etc. So this would be one of the ways. What is the next? If it is stable, let's say the person is alcoholic. Dana?
Yeah, I'm thinking. I don't know.
Well, actually, hemodialysis might help too.
Also, in this.
Yes, because we can adjust the diluents in the hemodialysis, and by this adjustment, we can reduce the number of ammonia. But something else that is much more radical than hemodialysis, what could you suggest?
And perhaps other medications that might help to convert ammonia into urea, and
it's usually done by the enzyme, because this conversion, because CO2 is highly stable molecule, and you would want to have some enzymes. I'm not really sure if we give enzymes to, in the bloodstream. Of course, they can create lots of problems, but without this kind of extracorporeal synthesis of urea, what you could suggest? Something very radical in terms of treatment.
very radical. Also transplantation, if it's.
Of course. So you could transplant some part of the liver. You don't need to transplant whole liver. The cool thing about liver is that due to evolution of this particular organ and working with lots of toxins, etc., it can regenerate from a very small piece. Okay, so let's say that you take one small piece from the relative so that the person does not have the transplant rejection, and you transplant it to the place after removal of the non-functioning liver. So what happens with time, this liver will grow, and it will be almost the same as the usual liver. It might actually be a little smaller, but it does not matter, because we need only a small part that would take the function of decontamination here. Okay, it is very radical, because again, in transplantation, the person should take lots of cortisols to really suppress the immune system, not to have the rejection of the transplant, either liver or kidney. But still, the person still lives, right? Because this is what we aim to help the person to survive. Otherwise, you all know that in previous centuries, when person would have these symptoms of hepatitis, etc., almost all the time they were considered already dead. And of course, this does not reflect the today's picture of the medicine, etc. So nowadays we could do transplantation, we could do the hemodialysis, etc., to correct the levels of ammonia, urea, or any other toxins in our body. Okay, so this is about the urea. That's why we use it on our cells, because if we have constant concentration of urea, the cells, they will die. And we want to understand how they die, at what concentration, at what time points, etc. So now we have 3 tasks. Really simple tasks. That's why we are going to talk to people, so 1 person per task. Okay, so we have Ayjan. Toliboy.
Yes, I'm here.
Could you please speak louder because I don't hear you?
Hi, I'm here.
Okay, nice. So you have the first task and you have the needed concentration, needed volume, and molecular weight. So what is the formula first and how you calculate the needed mass of the urea that you need to solve?
So the main formula is C concentration equals to N divided by the volume.
Okay.
And from that, I can find the N is equal to the mass divided by the molecular weight.
Okay.
And here
so,
I need to find the mass.
okay.
It equals molecular weight multiplied to the N, to the mole. And I have to put this instead of the N in the first formula.
Okay, so what it would be?
It will be S equals to molecular weight multiplied to N divided by volume.
Just a second. So you said C equals.
It equals. Так. Ой. I got confused. So it equals to M divided by mass divided by molecular weight. Yeah, to volume.
Okay,
Multiplied
nice.
volume.
Yes. So you need to find this mass. So what it is?
To find this mass, I have to multiply the concentration 0.1. Yeah,
We are talking about more formula now. Okay, so concentration times
molecular weight to mole to N.
mass.
And now we have to put the numbers. Oi. Так, not the N, but the volume.
Yes, of course, volume. Okay, so this is your mother formula. And now you just put all the stuff that you know, and you know everything here. So what it would be?
0.1 to 60, 0.6. And we have to convert the milliliters to the liters. If yes, then it will be multiplied to 10.
It's not if yes, you are telling me what to do. Right? Okay, so you convert it. So what it is?
10 to the power of minus 3.
10 to the power of minus 3. Okay.
And it will be 6.006 multiplied to 10 to the power of minus 3 grams.
Where does this gram come from? I
From
don't see
molecular
any
weight.
measure. I don't see any measure units here. So if you don't have measurement units, you might really make a simple mistake that will lead to incorrect answer. Please don't forget about these measure units. Okay, so what they would be in this equation?
So 0.1 will be it will be mole divided by the liters. And next it will be gram divided by moles. And the last will be the liters.
Okay, nice. So liters, they cancel each other, moles cancel each other, and we're left with gram. So why do you need these measurement units? Because it is a simple checkpoint for the calculation. If your mass is measured in grams, then most probably everything is fine, and you should be able to reach the correct answer. If it is, I mean, after your cancellations, etc., if it is 1 per gram, then of course it's not right? I mean, don't forget the measurements, because otherwise you will easily make a mistake. Okay, so now we understand where this gram comes from, and we are left with, if you want to remove these powers, what would you do?
I'll have to write differently, like milligrams.
Oh, yes, of course. So how much is that?
It's 6.66 milligrams.
Yes, of course. So this is the answer to the first task. Okay, nice. So the next person. And we are talking to Nurgisa. Nurgisa. And Nurgisa is absent too. So we had Karina and Nurgisa, right? So this is not right, guys. If you logged in, if you look online, please be online. So Polina, second question is yours.
Hello.
Hello.
To make one more solution.
We start again with formulas, okay?
Okay, I just want to read it one more time.
Nice. So you have the volume, you have the concentration, and of course the molecular weight does not change.
So it's like just different numbers, but the idea is like as in the first question.
Yes, yes, of course. So you are preparing different concentrations of solutions for your experiment, and now you just make the calculations.
Okay, so I have the concentration and I have the volume, so I have to find n. So the formula, the initial formula will be n is equal to, oh gosh, my brain suddenly stopped working.
Okay, so let's start with a simple formula that are related to C and V. So what you could find from here.
So the C is n divided by V. If we there, then C multiplied by V, so concentration multiplied
Yes.
by volume. And well, I have the concentration is just 1 molar, so it's 1 mole per gram. No, per decimeter cube or per liter.
Per liter, yes. Times.
Okay. 1 milliliter that I have. And okay, I need to make it either 2 liters in both cases or 2 milliliters. Okay, so I can write, instead of liter, I can write 1,000 milliliters instead of liter.
Here?
Yeah.
Okay. Okay.
Yeah, and multiply by 1 milliliter, so it's 10 to the power of -3 moles.
Yes. Okay, so milliliters cancel each other and we are left with moles. So amount of substance is measured in moles. That means that we did everything right or correctly. Now we have amount of substance, which is 10 to the power of -3 moles.
Yes, and I have the molecular weight, 60.06 gram per mole, so I just multiply.
Okay, so what do you get in the end?
I get 0.06006 grams.
What?
Grams.
Grams. Okay, so what is this thing? If you think about the concept itself.
This is mass.
Yes, of course, mass. So the mass formula is equal to n times molecular weight. Or in other words, the n or substance amount of substance is equal to mass divided by molecular weight. So whichever is taken, it gives you the power to identify the mass. And here you get these grams, but you just don't like these zeros and decimal points. So you convert it to something that is much more comfortable. So how you do that?
6 multiplied by 10 to the power of -2.
Okay, so 6 10 to
I
the
can
power
write
2.
6. Yeah, but there should be like 6.006. But if we just make it like rounded, then like this.
Okay, so now you want to remove the powers.
Oh, you want me to say milligrams or something like
Yes,
that,
of
right?
course.
Okay, then we can write 60.06 milligrams.
Yes, of course. So this is a much comfortable units than using this guy or this guy. And of course, again, when you say this formula, how to say that? Again and again, when you repeat it, it will create those automated ways of your neural networks. And in the end, you will not get lost in the calculations, okay? So please do these repetitions every time. So even if you could use the formula from the previous task, just redo it because it will help you in the end, okay? Polina, it's all right here, 60. So we had 6.006 milligrams. Here we would have 60.0006 milligrams. Now the last question. So who do we talk to? Okay, so Nurgisa, I got it. And we're talking to Yildana. Hi. Could you talk? Well, okay, I see your mic does not work. Okay, so we are talking to Alihan. Alihan, do you have
Yes,
a
yes.
working
My
mic?
microphone
Okay, nice.
is everything correct.
Okay, nice.
So first of
So-
all, concentration is equal to mole over volume, T over V, N over V.
Okay, again, concentration is equal to
N over V over volume.
N over V, yes.
Yes. N in our case equals to mass over molecular weight.
Okay,
Yes. So we can, from that, we also know that N equals C multiplied by V.
okay, nice.
So if we substitute N in this scenario with
Okay,
M over molecular weight,
okay,
mass will be equal to molecular weight multiplied to CV.
of course, yes, absolutely right. So now you do the calculation.
Yes. Molecular weight 60.06 gram mole.
Yes, this guy.
Mhm.
Okay.
Concentration is 3 mole, 3M.
No, we cannot
mole
use
over,
this.
yes, mole over liter.
Yes, okay. Times.
And our volume is 1 milliliter.
Okay, nice.
Yes, which we can convert to 10 minus 3 liters.
Okay, so let's write it like this.
Yes.
Nice.
Now-
So what cancels each other?
Moles cancel each other and liter cancel each other.
Okay, so
So
we are
we-
left with,
There's only grams.
yes, of course, and mass is measured by grams. Okay, nice.
So 180.18 milligrams.
Milligrams. That is nice, but again, as in previous tasks, first you get the mass in grams and then you convert it to milligrams, okay?
Okay.
So if you just do this calculation, you don't get 180, you get 0.118
Yes.
grams, and then you convert it to your milligrams. That is nice, and we are left with the real numbers that we're going to use for our experiment. It is again just to remind you the importance of all those formula, of all those calculations. You think that you know everything, but at the needed time, it actually strikes you and you just don't know what to do. Or you know what to do, but you make a mistake because you miss one simple step. Okay, so now let's talk about the procedure. As you remember, we add 10% of the final volume of Alama Blue. So now we talk to, I guess I talked to everyone here, right? So Aigirim?
Yes.
Okay, no, we have these 50 microliters as 10% of the volume. What is the final volume?
500 microliters.
Yes, so this is your final volume, and it is made of the volume of urea in DMEM and the volume of Alama Blue. So for 50 plus 50 microliters. Okay, so I hope you understand how we got these numbers, because it is 10%. Okay, so what we do everything in a tissue culture hood. Otherwise, you have a chance to contaminate your incubator, because you do use incubator in this experiment. And if you contaminate it, then there are lots of problems for everyone in the lab. So please don't do that. If it is needed to be done in the tissue culture cabinet or hood, please do it there. Okay, so as we said before, we add the urea in complete DMEM. So urea plus complete DMEM, and complete DMEM for the cells to live. Okay, so you add them after you remove everything from the well. And after this addition, you incubate it for 30 minutes because you want cells to adjust to the new conditions, to the new environment that includes urea. And after 30 minutes, when they feel comfortable, you add Alama Blue, which is 10% of the culture volume, and you go to your measurement of the fluorescence. So why do you want to do that? You want to have a snapshot of 0 hours. And in this case, of course, you understand the initial setting for your experiment. Okay, so after 1 hour, you have another measurement of fluorescence. The best would be, of course, see the dynamics of Alama Blue reduction. And let's say that you make it at 1 hour, 2 hours, and 3 hours. Of course, in this case, you will obtain a very good linear representation of the growth of your cells, and it will give you much more information. But again, this experiment also involved some problems with PC. That's why we don't have the initial, where is the initial here, initial measurements, and we're only left with 24 hours. It is still okay because you could perform some kind of analysis on top of it. But in terms of better picture, we lost these 1 hour and 0 hour measurements. Okay, so schematically, we have treatment for the cells, so addition of this urea. Then we add Alama Blue, and we incubate it and use the VarioScan to measure the intensities of the fluorescence. If you don't have the VarioScan, but you do have the absorbance measurement for the plates, so usual spectrophotometer, you could use it too, because again, Alama Blue is universal because it has both change of color and intensities of fluorescence. That's why it is so good and nice for scientists. Okay, so what do we do here? We analyze the data. So I think this everything will be explained on the next slides. Yeah, somewhere here, but let's talk about it first. So if you remember, we were having these A/B controls as our blanks. Blanks. Okay, so why? Because the oxidized Alma blue has some background intensity of fluorescence, and we want to extract it from all of other measurements. And in this case, of course, we obtain a very good picture of our experiment and the treatment itself. Okay, so we have it as a blank or autofluorescence signal, and we would want to have the mean of it. So you remember that we had 3 measurements there. So we take the mean, and we take mean as addition of value 1, value 2, and value 3 divided by 3, because three values are accessible. So we get the mean, and then we calculate the standard deviation. Standard deviation is the square root of value 1 minus mean squared plus value 2 minus mean squared plus value 3 minus mean squared. These all we divided by 3 and take a square root to obtain the standard deviation. Why do you want to have standard deviation and mean? Because you want to calculate the coefficient of variance given in percent. And it is calculated from standard deviation divided by mean times 100%. So you want to know these coefficient of variance because you don't want to calculate the outliers. And in this case, deviating values are outliers, and you want to exclude them from your calculations. Okay, so you calculated all those stuff. You know the mean of your blank, and then you are going to start with the calculation of your values for each of the treatment in the experiment. Just a second, guys. I hate sneezing, so I don't want you to hear it. Okay, so we have the percent in the Alma blue reduction, and you want to reflect it on the graph for each of the treatments. So what you do, you have the graph, okay, and you have 4 different treatments. So first one is 0 molar concentration of urea, and it is going to show you the maximal metabolism that is possible for this cell type. Because you use the same seeding density for each of the wells, for each of the treatments, of course, it will show you the maximal non-toxicated metabolism. And of course, in 3 molar concentration, you will have the least metabolism because you actually kill cells there. So what you do, you find the mean for the untreated control after you have the correction of the fluorescence intensities. So let's say that you have 3 different values, okay, so 1.1, 1.2, and 1.3. And you know that the blank is actually 0.3. So what you do, you subtract the 0.3 from all of those values, and you're left with corrected fluorescence intensity. So in this case, 0.8, 0.9, and 1. So then you have the mean of it, and mean would be 0.8 plus 0.9 plus 1, and gives you 0.9 in total for your mean, okay? So this is your untreated control corrected for the blank. So you're going to use it to identify the percentage of difference in Alma blue reduction. So here you have this percent, here you have concentration of the treatment, so for urea. So if you take 0 molar concentration, of course, the percent or percentage will be lying on the y-axis. And so 0.9 divided by 0.9 times 100% from this formula gives you 100%, right? And it's going to be somewhere here. Then you calculate all those corrected fluorescence intensities, and you have the means. After that, you put the mean here, and you're untreated in the divisor. So it is going a little messy. So let's do it again. So after you calculate the means for your treatments, you're going to put them in the denominator, and in the divisor, you have the untreated control. And of course, you have the ratio of the survived cells, and it will look like this. Okay, so we assume that this is 1 molar, this is 0.1 molar, and here we have 3 molar concentration. And of course, you see that we have some kind of graph that represents the cytotoxicity of urea. Okay, so if you have many different concentrations, the graph would be much more precise, and most probably you will see something like this, okay? But because we don't have much values in between 0 and 3 molar, you will not see this kind of bending here. You will see just straight line like this. But of course, you should understand that it is going like in this graph. So here, because the scientists, they used many different actinomycin concentrations, they could see this gradual increase of the cytotoxicity. So here you have 20% survival of the cells on this concentration of the actinomycin. Okay, so this is how you interpret the results, and that is why the cytotoxicity tests are very important for you, because if you have this graph here, of course you will not be using these 10K nanogram per milliliter in your experiment, because you would expect only 20% of the cells survive this treatment. Actually, you would go less than 50 nanograms per milliliter, because here you already have 45% survival of the cells at this concentration. Well, I don't know what is this article that the graph comes from, and I don't know the purpose of this experiment, but the best would be using 0 nanograms per milliliter or no treatment control to identify the highest possible survival of the cells, because it just gives you the better understanding of how the cells behave. Okay, so here on this slide, you see the logarithmic distribution of the concentration of the drug. And with this logarithmic distribution, you understand at what concentration you have the 50% death of your cells. Why would you want to know it? Because it actually tells you much about the cytotoxicity. So the 50% death for these cells is somewhere between 8 and 7, so 10 to the power of 8 and 10 to the power of 7 molar concentration of this particular drug. It means that with the increase of this molarity, we will see more and more cells dying. And of course, this drug cannot be used at these concentrations. I think the best again would be going as low as 0 concentration to understand how the drug behaves. But this lethal dose 50 is a very speaking argument in your research, because if you have high concentrations, it means that, if you have very low concentration that already kill 50% of your cells, it means that this drug is almost certainly will not be used as the treatment for people, if we talk about the medical pharmaceutics. Okay, so here, again, just because we had some failure of PCs, we don't have the picture of the real 24 well plate, but we have picture of other cells. So in this case is A549 and NERC cells that were having the same cytotoxicity test. And as you can see, the NERC cells are much higher in the metabolic activity than A549, because these guys, they were not treated with the urea, but of course, in these NERC cells, they converted much more Alama blue to pink than their neighbors A549. Okay, so also you could see that this urea was killing much more NERC cells than the A549. Well, it's just kind of arbitrary or results that are seen by naked eye, but if we go through the calculations, the most probable outcome would be that at 3 molar concentration, NERCs die very fast, while A549, they kind of resist and endure the treatment. Okay, so we have here the datasets. So we have 2 datasets that are related to 24-hour measurement of the treatment. So here we have already calculated the blank for your cells. So the blank is 1109. So what you do, you take all those guys for each of the datasets and you subtract 1109. So very fast. So here you have 92, 24, 8, and so on and so on. So you just first correct the fluorescence intensity and obtain corrected fluorescence intensities. Then you perform the mean calculation. After the mean, you perform standard deviation and CV coefficient of variance in percents. You understand if you have any outliers. If you don't have outliers, you just go on with the calculations. And after you've done this part here, you start building your graph. And again, for your graph, you have percents of metabolism of your Alama blue against the concentration. In your concentration, you have 0.1 molar concentration of urea, 1 molar, and 3 molar concentrations. Okay, so how you calculate this guy here? You take A row as the untreated control, and you obtain its mean, okay? And the mean here is about 90 units of intensity, okay? So what you do, of course, you have 100% at 0 because it's the maximum that you could achieve for this particular measurement. Okay, so since you have this 100%, you draw it as 100 on your y-axis, and then you calculate this same stuff, I mean the mean for your B row, and then you divide corrected mean of B by corrected mean of A, multiply it by 100, and you get the relative answer for putting it on your graph, okay? So let's say it's about 80%, right? So if you look at this difference here, it's kind of close to 80%. So it means that on your 0.1, you have 80% survival of the cells. So this is your first point. Then you calculate the same for your C row, and the same goes, the same calculation goes here. So corrected mean of C divided by corrected mean of A multiplied by 100, and you have 25-ish%. So at 1 molar concentration, you have 25%, which is somewhere here. So this is your second point, and the third point is less than 10%. Oh, let's make it 10%. So here, and you have this graph like this. This is what you are going to do. And the same as in previous lecture, I hope you all received the announcement that you only need to show the calculation for one of the data sets, okay? But you need to draw the graphs for all of the data sets. The same goes here. So I want to see the calculations for dataset 2 or dataset 1, whichever you prefer. And then you draw the graphs for both of these datasets. Is it clear, guys?
Yes.
Nice. So you will have two graphs, but one dataset should be calculated. Okay, so this is my wanting from you. Okay, so here on this slide, you have a better explanation of what happened here. So how stuff was calculated. And of course, here you do all those calculations, you obtain the needed values for your graph, and you draw it. So it looks something like this. Of course, it does not represent the real distribution of the values because you have the same distance between these two points, and in real they are not the same, right? So this guy looks a bit like the logarithmic representation, but if you really do the proper graph here, you will need to draw 0.1 very close to 0 because it's closer to 0 than your 1 molar, and then 3 molars would be here. And of course, the graph here would be kind of distorted towards 0, and it will look more like this, okay? So I want to see the graph for dataset number 1 and the graph that is showing the real positioning of your concentrations, okay? And 3 is somewhere there. Okay, so this is what I want to see, plus the graph for dataset number 2, plus calculation of one of these datasets, either 1 or 2. So this is about the experiment. We actually are done with the questions, with the lecture. Now we are switching to the. What did I do? Okay, just keep it. Okay, so my PC is frozen. Do you guys hear me?
Yes.
Yes,
Yes, we can hear you.
Nice. Let me close the PowerPoint because it freezes my PC. And then we start with the questions. Nice. Okay, so we start with the questions. So, anyone?
Could I just clarify? So AB blank is the fluorescence at 0th hour, right?
0 No, AB blank is 0 cells, 0 treatment, which means it's clear or pure Alama blue. Okay.
Okay.
So you just don't add anything. You measure the real autofluorescence of your Alama blue. Okay. Okay, other questions? So we are approaching the finals actually, and the final, it will include some calculations. So do expect calculations there. I will make sure that I don't mess up again. Well, this happens. Of course, we're all a people, and it really should tell you that everyone can make mistakes. And there is nothing like super dramatic about making mistakes. It is the way of your brain to learn something. Okay, if you don't make mistakes, it means that you do everything perfectly. And if you do mistakes, it means that you need to adjust something. So mistakes are the representation of your weak points. And what is your goal in terms of studying in this university is to make yourselves as perfect for lab work as possible, right? That's why do mistakes, do not fear these mistakes, do not get scared by making mistakes, but if you made them, go back, troubleshoot them, and try to resolve them, because otherwise your brain will not learn, okay? Again, read the formula, learn the formula, and use the formula. Go to Google, find all those thousands of concentrations, tasks in internet. They are easily accessible, and please solve them, because it is the main part of your future work. So I hope it was also clear. Sorry. Do we have any questions? Nice. Then I will be expecting some questions over email. And when we stop, I will just go and correct your quiz marks, because again, if it was just the problem of understanding, etc., you wouldn't have these additional points, but now it's my mistake. I made them wrong, incorrectly. That's why I'm going to change them to full marks. Okay, so I will see you next week on the demonstration of image J. So have a nice weekend. Goodbye.
Goodbye.
Bye.
Goodbye.